All right, good afternoon. Load line analysis. Does anyone have any questions? You all ready to take a pop quiz? Somebody said yes. Somebody said no. All right. Let's see. Yeah, we stopped here. Okay. Any questions about load line analysis? Okay. Then let's look into the second method of determining our diode voltage and current, the operating point. And that would be the mathematical model. So we are given that a diode has saturation current IS value of 10 raised to minus 13, and non-ideality factor is given as 1, asks us to use thermal voltage of 0.025 volts. Determine the Q point, meaning we need to find VDQ and IDQ. Our circuit is still the same. As a refresher, if you don't remember, you had a voltage source, resistance of 10 kilo ohms. This is our diode. 10K, 10 volts, results in current ID. And diode voltage VD to appear across that diode. All right, so in this, what do? We can write one equation for ID. This N is plus 10. This is VD. So if you apply KVL,
I thought you were about to kick us out.
we can write 10
Some girl went
volts.
over there. It's like this is a
And if
research.
you log on online, please make sure you're muted. All right, so if you apply KVL, you get 10. No need to apply KVL. We can write a current equation directly. So we can write ID is equal to 10 minus VD over 10,000. That's one equation that we have.
Oh wow.
A picture.
That was another one. All right, 10 minus VD over 10,000. Now, as with the load line analysis, we need two equations, right? We have two unknown variables, so we need two equations. We have one equation from the circuit. The second one we can obtain from the diode equation. And so we can write ID is equal to IS to E raised to VD over VT minus 1. I'm going to ignore the N because N is given to us as 1, so I'm going to ignore it. Well, ignore it in the sense that if I plug it in there, it's just 1. So it doesn't make any difference. All right. Yes. Good question, actually. The reason I'm using it just a little different is just so because we are using two different equations, but essentially they're the same. Yes. So the question being asked was, is this ID and this ID, are they the same? The answer is yes. But because we're using two different equations to find them, I just wanted to differentiate between the two. All right. This is N is equal to 1. Also, to just simplify it a little bit further, because this is 1, I'm going to ignore that too. The answer is going to be approximation, right? So ID is approximately equal to IS into E raised to VD over VT. All right. So now what can I do? If I transform this equation, I can write VD is equal to Vt times Ln Id over Is. Okay, Id over Is. And now what I can do is I can plug in this ID into here. So plug into that equation, and that results in obtaining a VD of Vt Ln 10 minus Vd over 10,000 times Is, 10,000 Is. So solve this equation, you'll find Vd. Calculators out. And see some narrowed eyes and some bored faces. This is a transcendental equation. It has logarithmic function in it, but there is no closed form solution that exists. We can't find it directly. We need a starting point. Okay. So let's not spend too much time on it. And I'll explain that we don't have a starting point, so we need to pick a starting point, right? We have no idea whether it works or not. We pick a starting point, meaning we pick a value for Vd and you solve the equation. So plug in Vd is equal to 0. What answer do you get for Vd? If you plug in Vd is equal to 0, what answer do you get? 0? Not quite. So the point of this exercise is that since this a direct solution does not exist, so we pick a point, right? We are assuming a value. Anytime we make an assumption, what do? We make an assumption, we go through our analysis or calculation, whatever the case may be, and then we verify the end result. Does the end result match with our assumption? If we choose Vd is equal to 0, the answer must be equal to 0. Then 0 is the right answer. But if it's not 0, that means that is not the right answer. So what did you obtain? Did anyone obtain anything? Okay, great. So now you plug in the answer you obtained because your calculation told you that your assumption is incorrect. I can't. I mean, if someone else is smarter than I'm like, my math skills are not as good as yours. I'm telling you up front. So I don't think I can solve this directly. Also, what we have learned is a technique called as iterative analysis, because this is a transcendental equation with a logarithmic function. So a closed form solution does not exist because there is VD on both sides of the equation. And even if we open this up to get VD on the other side, it's not going to work. To open the log, we got to take exponent of the VD on the other side. So we are in that same situation. So we need a starting point, and there is no starting point available. So starting point would be to assume a value for VD and then solve that equation and see if the result for VD turns out to be the same as our assumption. So we assume value for VD, plug it into the right side of the equation, and solve for VD, or solve the equation for VD. And then at the end, we ask ourselves the question, does the resulting value match our assumption? Okay. Does it match our assumption? Yes, then you're done. No, go back to the top. And you keep doing it until you get a yes as the answer. So this process is known as iterative analysis, mathematical solution. So I heard several students say you obtain 0.5 something as the answer, right? So you can plug in 0.5, run the calculation again, see what the answer is. And you keep doing so until your assumption and your end result match up. Now, you don't have to do it now. I'm just going to explain how it is so easy to do it with a computer nowadays, right? So on here is something I programmed. I programmed this in Excel just to show you separate results. Obviously, we can just program the equation, picking a starting point, can solve it in MATLAB or Desmos or any equation solver. But let's say I did this. This is my initial assumption. And I obtained 0.594 as a result. Okay. So I chose VD as 0 and I solved that equation, meaning I could plug in 0 into that equation and I solved it to see if I get VD is equal to 0. Didn't turn out to be the case. I got it as 0.59. Okay. I obtained 0.59. Then I just want to show what happens if I choose a random number. I know, let's say I don't know whether this is a silicon diode or not, right? No other information is given. Doesn't say it's germanium, doesn't say it's silicon, doesn't say it's a LED or gallium arsenide or whatever. Let me assume it's silicon diode. Let me plug in 0.6 or 0.7. In this example, I plugged in 0.65. So if I plug in second assumption, 0.65, I obtain an answer 0.59233. What does that tell us? The answer is somewhere close to 0.59. So this is result of second assumption. Okay, that's the result of second assumption. And now what do we do from there is you take that result and you solve it again. So you're iterating. It's an iterative process. You keep going over and over and over until your result matches up with the assumption up to your desired decimal places. If you're just taking 2 decimal places or 3, get the answer very quickly. In this case, the initial assumption 0 is just to explain to students on what we get. I would not start with 0. I would typically start at 0.6 or 0.65 or 0.7, either one of those 3 values. Okay. So let's say I started here and then I obtain the answer here. This is the result of third assumption. You take that and you run it through. You can already see within 2 steps or 3 steps, my answer is coming out to be the same. You see that? Going all the way up to, let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Up to 6 decimal places, my answer matches up. I can put a stop to this process right here and say my diode voltage is 0.592491 within just like a couple of iterations. Okay. But if I want to continue going, I can keep going. I can find it. And finally, this place or this spot, I get the exact same answer as my input. My input is up to, let's see, 8 digits, 8 decimal places. My answer is exactly the same. And just to verify one more time, I plugged it in. Obviously, shouldn't change. Get the same exact answer. Okay. So if a solution does not exist, we cannot solve it with normal means. We make an assumption on this model. We make an assumption, solve that equation with that assumption, verify if our answer matches up with our assumption. If it does not, we go back to the top, we make a second assumption, and we do it again and again and again until our answer matches up with our assumption. So you have to go through several iterations. Hence, this is known as an iterative process. All right, let's take a pause, write it down, think over it. Let me know if you have any questions. By the way, after you program this in a spreadsheet, I mean, it takes less than, yeah, it's just a click and you get the answer. Yes. Yes, that's fine. Question being asked was, can we use a spreadsheet on the test? And the answer is yes, if you want to. Yes. This open book, open notes. Same standard as the quizzes. Yes. Equation solver, you plug in the values that are in the fourth or the last column. 574. Okay. Okay. So maybe there might be an error in something that I'm doing, perhaps. I can take a little later, but if both of you are getting the same answer, then maybe there's an error. Or maybe I used slightly different values, perhaps. I don't know. And it's to minus 13. I don't know. I can take a look. But any other questions on the iterative process? Okay. Mathematical model. All right. Somebody on Zoom, please send a test message on the chat. Thank you. All right, so here we now come to the ideal diode model. Expect a question based on the ideal diode model on the final exam. I'm letting you know right now. One of my favorite topics to go to. Also one of my favorite analysis techniques. So if I have a diode circuit and I wish to analyze it, I use the ideal diode model, very quick and easy analysis. Well, wouldn't say easy, sorry, quick and straightforward analysis. Okay. What do we do in the ideal diode model? Well, we make an assumption. The assumption is that if the anode of a diode is at a higher potential than the cathode, the diode is forward bias and the diode is on. Okay. So here it says ideal diode symbol, meaning it's a diode enclosed inside a square. Not often seen this kind of symbol. Okay. Or simply just state, okay, ideal diode model, and then it would be a regular diode symbol. Okay. So ideal diode model is basically if the anode is higher than the cathode, the diode is on. It's a short circuit between the two. And if it's off, then it's open circuit. So I will write down SC and OC. Okay. This is diode is forward bias. If cathode is higher, then it's reverse bias. Okay. So in forward bias, the diode characteristic for an ideal diode is that in forward bias, you have current and voltage is equal to 0. And in reverse bias, voltage is negative and current is equal to 0. So let me write it out. Let's say you apply a source voltage. Source voltage is greater than 0 volts. Diode turns on. Diode is forward bias. We say the diode is on. You replace with a short circuit. Okay, short circuit. Under these conditions, under these assumptions, under these conditions, our diode voltage must be 0 volts. And our current ID must be greater than 0 amps. Okay. If it's on, it's conducting current. So current must be positive. Again, numerical, mathematical, sorry, not mathematical. It's a model that we are using for quick analysis of our circuits. So in these models, we are making assumptions. Ideal. No such thing exists in the real world, right? It's an ideal model. So it doesn't take much voltage for it to turn on. We could say it's 0.00001 volts higher, or anode is 0.0001 volts higher than the cathode. Diode is on. It doesn't require any voltage to turn on. Simply the fact that anode is higher than the cathode, diode is on, and it's replaced with a short circuit. And if it's a short circuit, that means diode voltage between the anode and cathode must be equal to 0. And current should be going in the forward direction. So VD is 0 and ID is 0 amps. These are the conditions you would check at the end of your analysis. Okay, or verify at the end. If your diode voltage is not 0, or if your diode current is not greater than 0 amps, then your assumption is incorrect. You have to go back and modify your assumption. Okay. So again, if you assume that your diode is on, then you have to verify these two assumptions. Yes. Sorry, what? Forward bias, reverse bias. In reverse bias, the diode is off. We replace with an open circuit, which means that our cathode is higher than the anode. So VD must be negative. It must be less than 0 volts. There is no other possibility. Also, ID must equal 0 amps. If it's reverse bias and it's open, there is no current flowing through the diode. So ID is equal to 0. And this is something, again, you check at the end. Let me write down verify. Verify at the end. Okay. So we have our assumptions. We go through analysis. We obtain some results. We need to verify whether the assumptions are true or not. So we compare them with our assumptions at the top. Again, if they are not matching up, or if they do not match up, then we modify our assumptions and we redo the process. Okay. Any questions? All right. Let's look at that circuit. So we had 10 volts. Ten kilo ohms. We had our diode, right? Now, this is a straightforward circuit, so it's easy for us to make an assumption. Let's assume that the diode is on. If the diode is on, replace with a short circuit. Diode current ID is flowing through the circuit. And therefore, we need to verify whether ID is greater than 0 or not. Yes. So the question being asked is, why do we have resistors in series with an LED? Yes, and also apart from that, without resistors, we cannot control the current at all. So any kind of circuit, if we wish to build any sort of circuit, we always have resistors in series. It is possible to power LEDs directly from a battery, but in the lab, so in the battery, voltage is fixed. So it's a, let's say, 1.2 volt LED, and you connect a 3 volt point cell to it. It's easy. Current is automatically limited, okay, because the voltage is limited. So if you design a circuit that way, you might be able to get away without using a resistor. In the lab, however, we have these benchtop supplies. It's very easy to over supply voltage and current to the LED. So the answer is yes, to limit the current. Okay, so we need to verify whether ID is greater than 0 or not. So we apply our circuit analysis techniques and determine ID. What is ID? ID is the same current that's flowing through the circuit. We know that the diode voltage is 0 volts. So if it's 0 volts, then 10 volts appears across the 10 kilo ohm resistor, and simply 10 divided by 10,000, or I would say technically 10 minus 0 over 10,000, which gives me 1 milliamp. Diode voltage VD is 0. And so ID is simply 10 minus 0 over 10,000. And we realize ID is greater than 0. Hence, assumption is verified. And so our assumption is verified. Or our assumption is valid. Okay. Does it make sense? Okay. One thing I'd like to point out is that all of these semiconductor devices will have different models, but the circuit analysis techniques are still the same ones that we learned in circuits 1, 2, and 3. Circuits 1, to be more technical. All the circuit analysis techniques that we use are from circuits 1. Okay. All right. What if the diode was reversed? What would our assumption be? So let's, oh, all right. Diode reversed. What would you assume the diode state to be? Yeah, assume that diode is off. If it's off, actually not there, then my circuit looks like this. Diode voltage is always measured with positive reference at the anode, negative at the cathode. So positive anode, negative cathode. So what is VD in this case? It's open circuit. So one thing is for certain, there's no current flowing through. If there's no current flowing through, there's no voltage drop across that resistor. If there's no voltage drop across the resistor, it means both ends of the resistor are the exact same voltage. So if you apply 10 volts at one end of that resistor, you'll obtain 10 volts at the other end, meaning it's minus 10 volts. And if VD turns out to be negative, that means our assumption is correct. Oh, just as a training exercise, instruction purposes. Like two separate case scenarios, that's all. Any questions? In both these cases, we made assumptions based on certain logic, based on circuit rules. It's a simple circuit, 3 components. Diode is connected to the the anode of the diode is connected to the positive terminal or closer to the positive terminal. So it's easy for us to make an assumption saying that the diode is on or the diode is off in the second case, right? But what if it's not so convenient? And we'll see that in an example. Well, if it's not so convenient and it turns out our assumption is incorrect, we need to go back and change our assumption. And the downside of this technique is that for n number of diodes, the total number of states that are possible is 2 raised to n. So one diode is 2 possible states, on or off. It was easy for us to make an assumption here, right? So 2 diodes, 4 possible states, 4 possible combinations. 3 diodes, Three possible states. Let's see, right here in this example. You have three possible diodes. No way of knowing for sure which one's on and which one's off. So there are three diodes. Therefore, total states, 8 possible states. Either all three are off or all three are on. Well, you've all studied the binary number system. 0, 0, 0, 0, 0, 1. If 0 is off and 1 is on, 8 possible combinations, right? 8 possible combinations. I will solve this example, but let's see. I probably can get into it today a little bit. But I'd like to point out a couple of important things. That just because an assumption is incorrect, okay? So in this example, we have D1, D2, D3, right? So let's say we assume D1 on, D2 on, and D3 off. Okay, just as a random example. So you have two diodes on, one is off. After going through our analysis, it turns out that D1 and D3 both valid, meaning D1 was on, D3 was off, but D2 was not on, so it does not match with our assumption. It does not mean that the other two diode states are confirmed. Again, I'm repeating. If we assume that D1 is on, D2 is on, and D3 is off, and at the end, it turns out that only D2 was incorrect, but D1 and D3 were fine, our assumptions matched up, we have to throw out the whole assumption. And we have to pick a different combination. It does not mean that half our assumption is correct and the other half is incorrect. Okay, if even a single diode out of the three is incorrect, that means all three are incorrect, because we don't know which combination is right. So anyway, that's an important point to keep in mind. I don't think we'll be able to get through that to that problem today. All right, so that was ideal diode. After ideal diode, we have the constant voltage drop model. Very similar to ideal diode. The only difference is that in a constant voltage drop model, we incorporate the real life diode voltage drop. Okay, it's still a diode voltage. It's still ideal diode model, but we need to apply a voltage to turn on the diode. So in reverse bias, this is exactly the same as ideal diode. Okay. In reverse bias, this is exactly the same as the ideal diode. No change. The only thing is that in forward bias, it requires certain voltage to turn on. That voltage could be 0.6, 0.2, 0.3, 0.7, depending on what kind of diode it is. Okay. If nothing is provided in the problem statement, you can make your own assumption. For the most part, I think in the book, it uses 0.6, so we'll stick with 0.6. Otherwise, the question would explicitly state, use constant voltage drop model, CVD model, with a diode voltage drop of 0.6 volts. Okay. So 0.6 volts. So all we are doing in this is we are adding the turn on voltage to the ideal diode model. And we are adding the turn on voltage to the ideal diode model. For silicon, it's typically 0.6. For germanium, it's typically 0.2. As I said, if it's not explicitly stated in the problem, Feel free to use your own. So in reverse bias, it's open circuit. In forward bias, because it is holding a constant voltage across its two terminals, we can model it modeled as a voltage source. Okay, with a value of 0.6 or 0.2. 0.6 or 0.2. Let's take a pause. Let me know if you have any questions. Good. Right. If it's forward bias, it can be on. I mean, it can be off. Oh, okay. So now I get your question. So if it's forward bias, but the voltage is less than V on, then it would not, well, I already gave half the answer, but then it would not turn on. So the key point here is that a turn-in voltage must be applied. So it's not just zero. So the anode must be higher than the cathode by at least 0.00001 or whatever. Must be higher. If it's exactly the same, it's still off. If it's 0.6 and 0.6 at both ends, then it's 0 volts across the cathode and the anode. That means it's not going to turn on. So in our example, we had a 10 volt source, 10 kilo ohm resistance, and we replace it with a CVD model. So this is 0.6 volts. So now our diode current is 10 minus 0.6 divided by 10,000. Instead of being 1 milliamp, it's going to be 0.94 milliamps. Okay. Ten minus 0.6, 9.4 divided by 10,000, so 0.94 milliamps. Make sense? Right. So after solving all this, let's take a look at a comparison of all the 4 techniques. I'll give it a few more seconds, wait for people to write it down. Okay. All right. So we use 4 techniques, right? It's load line, iterative, ideal diode, constant voltage drop. Let's first look at the diode voltages using the 4 techniques. Constant voltage drop, we are told to use 0.6, so we use 0.6. Load line was an approximation. We still approximated at 0.6. Mathematical was the most accurate. So 0.592, still not too much of a difference, 0.59 and 0.6, right? Ideal diode, of course, is the only large variation, but that's because of our assumption that it only requires 0 volts. Otherwise, it's not, I mean, it's not, kind of like a weird result in that sense. If we were just using 4 different calculations and we got 0 and 0.6, we would say, yeah, they're too far off. But in this case, the ideal diode itself requires the assumption of 0 volts. So that's because of the assumption. But look at the currents. Even though we chose 0 volts for our model, the current is not too far off from the rest of the 3 measurements or 3 calculations. 0.94, 0.94, 0.94, all 3 of them match up. Load line, perhaps we might have taken 0.95. But even if we took 0.95, we are not too far off. Okay. So all methods are pretty much in alignment. We can pick and choose any one we want. Ideal diode is usually used when you want to perform a circuit analysis and we just want to know how the circuit is working and what it is doing. Okay. Then if you want to determine the actual voltage and current, we would use a different model to verify our answers. I typically use ideal diode analysis to simply just look at what the circuit is doing, okay, and how it's behaving. All right, questions? No more questions? Okay. All right, we'll end class here today. We'll look at the 3-diode problem on Friday. Okay. So again, review the material as soon as you have the time so that you can have your questions prepared for next class.